Arduino, Session 1, Light. Before we begin, make sure to fill out the circuits in Arduino pre-survey. For this session, you will need a computer with strong internet connection and a Tinkercad account. The browsers that work best with Tinkercad are Google Chrome or Firefox. What are circuits? Electrical circuits contain conductive paths for current or electrons to flow. A closed loop means that current can flow, while an open loop means a current can't flow. In this example, the circuit on the left is open and the circuit on the right is closed. The LED on the left is off, while the LED on the right is on. Ohm's Law is a simple yet fundamental equation that can help us understand the basic relationship between current, resistance, and voltage. Voltage is directly proportional to the product of current and resistance, denoted by V equals I times R. This formula is useful when creating circuits with Arduinos. You can think of electricity as very similar to water to give you a better understanding. Once you are logged into the Tinkercad website, you should be able to see a screen like this. Go ahead and click Learn. We want to switch over to the Circuits tab, and then we want to click on Lessons. Go ahead and click on Ohm's Law. You'll find all of the instructions for Ohm's Law tutorial on the side on the left. Let's go over Ohm's Law real quick. In all circuits, electricity flows from the positive side of your power source, like a battery, to the negative side. The name for the flow of electricity is current. When current flows through a component, like an LED or a resistor, there is an associated change in potential energy across the component that is known as voltage. The amount of voltage drop across the component depends on its resistance, or how much it restricts the flow of its current. This can be really important for making sure your components don't fry because they aren't able to support the current coming from your battery, as we will soon see when it comes to parts like LEDs. These three concepts, current, voltage, and resistance, are all related to one another through a law called Ohm's Law, where voltage is equal to the product of current and resistance. Let's test this out. In the editor, you'll find a simple circuit connecting an LED directly to a 9-volt battery, as you can see right here. If we power the circuit, we expect that current will flow from the positive side of the battery through the LED and then into the negative side of the battery. Turn on the simulator to see what will happen to our LED, which is the Start Simulation button here. If you hover over the light bulb, you can see that we are pushing too much current through the LED, more than it can handle. So let's see how we can stop this from happening. LEDs have a maximum rated current level, or a maximum amount of current it can safely handle. In this case, let's account for a maximum current of 20 milliamps, a fairly standard rating for LEDs. That's 0.02 amps if we convert milliamps to amps. If we want to ensure that there is only 20 milliamps of current flowing through the LED, we need to add some resistance to our circuit. We know that the voltage we're applying is a 9-volt battery, so we can use Ohm's Law and divide 9 volts by 20 milliamps, or 0.02 amps, for 450 ohms. This means that if we want to ensure there is only 20 milliamps of current flowing through the LED, we want to add a resistor with a value of 450 ohms to our circuit. Go ahead and go to the components and add in a resistor, as you can see on the side right here. You can click on the resistor and change the value to 450 ohms. Add the resistor to the circuit by removing the red wire. You can click on it and hit the delete button. Drag the resistor in between. Take the positive end of the battery connected to terminal 1 of the resistor. I would change this wire color to red. And then from terminal 2 of the resistor, add another wire to the anode of the LED and make sure this wire is also red. And that's it. When you click Start Simulation, your LED will run with no problems. Series and parallel circuits. There are two different types of circuits, series and parallel. In a series circuit, all components are connected to each other and voltage runs along one path. In a parallel circuit, voltage can travel different paths and components in different paths are not connected. For example, if you removed one of the bulbs in the series circuit, the circuit would be open and the remaining bulb would be off. However, if you removed one of the bulbs in the parallel circuit, the remaining bulb would still be on because it is not connected to the other bulb. Therefore, the circuit would be closed. The example in the images shown here represent how series and parallel circuits differ for circuits with two light bulbs. In a series circuit, voltage is shared between the two light bulbs, so the two light bulbs are relatively dim. On the other hand, the two light bulbs in the parallel circuit are both relatively bright since voltage travels through two different paths. Because the bulbs in the parallel circuit do not share voltage, they are relatively bright. An Arduino is an open-source electronics platform based on easy-to-use hardware and software. Arduino boards are able to read inputs such as a light or a sensor, a finger on a button, or a Twitter message, and turn it into an output, activating a motor, turning on an LED, and publishing something online. A controller is a computer on a chip, optimized to control electronic devices. For our Arduinos, you can think of it as a mini, much simpler computer that allows you to control sensors and output devices and carry out your desired commands. The breadboard is made up of several discrete rows and columns that are connected. The rows are split down the middle, and the rows run all the way down each side. The rails are denoted by letters A through E, and the rows are denoted by numbers 1 through 30. Pins in the same row are electrically connected. Pins in different rails are not connected unless there is an external wire connecting them. The power plus and ground minus rails are special rails that are used to provide power or ground to the circuit. It is common practice to connect the power and ground pins on the Arduino to these rails.
Let's learn how to blink an LED using Arduino's digital output. If you're new to Arduino, this is a great place to start. You can follow along virtually using Tinkercad circuits. Then afterward, grab your Arduino Uno board and a USB cable to create a physical circuit. Take a look at this circuit in the workplane. Click Start Simulation to watch the LED blink. You can use the simulator at any time to test your circuits. The LED's legs are connected to two pins on the Arduino, ground and pin 13. The component between the LED and pin 13 is a resistor, which helps limit the current to prevent the LED from burning itself out. Without it, you get a warning that says the LED may burn out soon. It doesn't matter whether the resistor comes before or after the LED in the circuit, or which way around it goes. The colored stripes indicate the resistor's value, and for this circuit, anywhere from 100 to 1,000 ohms will work great. Click once to connect a wire to a component or pin, and click again to connect the other end. The LED, unlike the resistor, is polarized, which means it only works when the legs are connected a certain way. The positive leg, called the anode, usually has a longer leg and is wired to power, in this case coming from your Arduino's output pin 13. The negative leg, called the cathode, with its shorter leg, connects to ground. Did you notice the small LED flashing on the board itself? This built-in LED is also connected to pin 13 and is meant to be used for testing purposes without the need to connect any external components. It even has its own tiny resistor soldered directly to the surface of the Arduino board. Let's look at the simple code controlling the blink by checking out the code blocks editor. The code starts out with two gray comment blocks, which are just notes for us humans to read. The first blue output block sets the built-in LED high, which is Arduino's way of describing on. This output command will activate a 5-volt signal to connect anything connected to the specified pin. Next up is a yellow command block that waits for 1 second. Simple enough. So the program will pause while the LED is on for 1 second. Next, after another comment, is a blue output block to set the LED back to low or off, followed by another second-long pause. Try customizing this code by changing the wait times and clicking Start Simulation. You can even add more output and wait blocks to create longer flashing patterns. In the text editor, you can see the Arduino code generated by the code blocks. All the extra symbols are part of Arduino's syntax, but don't get intimidated. It takes time to learn to write proper code from scratch. I'll break it down for you here, and you can always use the blocks for reference as you level up. This first section is a block comment followed by the code's setup, which helps set up things your program will need later. It runs once when the program starts up. Our Blink Sketches setup configures pin 13 as an output, which prepares the board to send signals to it rather than listen. The main body of the program is inside the loop. This part of the code will execute on repeat, so long as the board has power. The colored text following double slashes are also comments to help make the program easier to understand. The output command we're using is digital write, which is a function that sets a pin high or low, on or off. To pause the program, we'll use delay, which takes a number of milliseconds. 1 second is 1,000 milliseconds. Try it for yourself in Tinkercad circuits. Grab this circuit anytime using the starter available in the components panel. To program your physical Arduino Uno, copy the code from the window and paste it into an empty Arduino sketch, or click the Download Code button and open the resulting file using your Arduino software. Plug in your USB cable and select your board and port in the Tools menu, and upload the code and watch the LEDs flash with the custom blink you just created earlier. Now that you know how to blink an LED using Arduino's digital output, you're ready to try other Arduino exercises that utilize the digital write function. Try using a breadboard to add more LEDs and code to control them in the next lesson. Thanks for watching and learning how to blink an LED with Arduino and Tinkercad circuits. Check out the rest of our huge collection of interactive beginner electronics tutorials and even build circuits into your 3D designs. See you next time.
An input device sends information to a computer system for processing. This means that it gives the computer data. Examples include switches, buttons, distance sensors, photoresistors, and etc. An output device displays the results of that processing. This means that the device receives instructions from the Arduino. Examples include LEDs, speakers, motors, etc. Imagine a circuit with a button, input device, and an LED, output device, where the LED turns on when the button is pressed. The button sends data to the Arduino indicating that it has been pressed, and as a result, the Arduino tells the LED to turn on. Arduinos use sensors as inputs such as a photoresistor, button, distance sensor, temperature sensor, and more to drive outputs like LEDs, speakers, or motors. But first, there must be some thought involved. The code we will write will be permanently installed on the Arduino, and it will have a fixed way of interacting with our outputs. It cannot learn. It only does exactly what we are telling it to do. Analog signals are like ramps. They are infinite in their possibilities. Digital signals are like steps. They have a finite set of values. Most commonly, digital signals will be one of two values, either 0 volts or 5 volts, meaning there is either no power or full power. Their graphs look like square waves. For example, for a range of analog values between 0 and 1, you can have values like 0.1, 0.001, or 0.0001, and so on. On the other hand, the digital values could only be 0 or 1. Session 2, Sound. In this activity, we will be building a buzzer. Go ahead and find a breadboard and drag it to your workspace. Then grab an Arduino and also drag it to your workspace. You will also need a potentiometer, and then search for a piezo buzzer. I'm going to place this piezo buzzer on the breadboard, and then I will place the potentiometer just a few spaces away in the same column. As you can see, they are both in column E. Then I will drag the ground here and connect it to the negative rail on the breadboard. I'll change the color to black. To make the circuit, we're going to connect the leftmost leg, terminal 1, of the potentiometer to the negative rail. We'll connect the leftmost leg of the buzzer to the rightmost leg of the potentiometer. We'll change this color to yellow to differentiate them. Then we will be connecting the buzzer to the Arduino pin 10. Go ahead and add this code to your coding block in the Tinkercad. If you want to keep the blocks and text feature so that it is easier for you to see how to code or why this code works, you can go ahead and do so, but for this tutorial, we'll be sticking to the text. We will start by setting a speaker pin variable to 10. This is the 10 that we connected our buzzer to on the Arduino. We are creating a variable so that it is easier to use and we know what we are referencing instead of putting 10 every time we need it. We always have a void setup function when we are working with Arduinos. The pin mode will be speaker pin and we'll set that speaker pin to the output. Then we have a void loop, which is our main function. This is where everything happens. Pay attention to the line numbers as you copy this code. We will initially have the happy birthday to you played twice with the exact same notes and beats, and pauses between. Then we will have a happy birthday dear your name, which will change slightly in the notes that we play and the beats that we hold them for. The pause will still be 2 beats, and then we'll finish off the final happy birthday to you with a different set of notes and a different set of beats. Make sure you pay attention to the line numbers once again. To make sure that this is continuous while we are playing the simulation, you will type in while true and then leave the brackets empty and put a semicolon. This means you'll get stuck in the loop. As you can see here, we had a play function that we called with a note and then a number. That is this helper function that we write here. We pass in a character, which is the note, and then we pass in a number of beats. We will have a variable called numNotes, which is the total number of notes that we have in our arrays. All of these notes are from C major so that we don't have to deal with sharps or flats. We'll have one array for the notes. As you can see, it goes from C to A, B, and then continues again in capital letters. We also have an empty beat here to account for the delay that we are going to use. We also have an array of frequencies that will match to the letters in the notes array. So C will match to 131, E will match to 165, and so on. We will have a variable current frequency in which we determine which frequency matches the one we want. A normal beat will be 150. So one beat will be this length. If we change this number to be lower or higher, we will be changing the tempo. Now, to look up the frequency that corresponds to the note, we will write a for loop that goes through all of the notes. As we declared above, there are only 14 notes, so it suffices for us to loop through 14 times. For each index in the notes array, so for each note in the notes array, we check if it equals the note that was passed into the play function up here. If it does match, then we set the current frequency, which was initially 0, to the frequency we can grab from the same index in the frequencies array. Then we play the frequency that we got using the tone function, which is a built-in function for the Arduino in Tinkercad. We will be using the speaker pin, the current frequency, and then we will pass in the beats times the beat length to get the correct number of beats. We will set a delay of the beats times the beat length so that it has time to play, and then we will have another delay of 50 so that the song sounds more natural with a few delays between. Here is a chart of all the frequencies and the notes that they align to. Session 3, Motion. In this activity, we will be building servo motors. Go ahead and drag a breadboard, Arduino, potentiometer, and a servo. Now, we want to connect the 5 volts pin on the Arduino to the power rail on the breadboard. I am going to change this color to red. We will connect this ground pin to the negative rail right here and change this color to black. Drag the potentiometer to column E on the breadboard. We will connect terminal 2 of the potentiometer to the power rail, as seen here. And then we will connect terminal 1 to the negative rail, as seen here. Connect the ground on the servo to the negative rail of the breadboard. Connect the power on the servo to the power rail on the breadboard. Make sure to change this wire color to red. Now we have a third component here called the signal. We will be connecting the signal to the Arduino pin number 9. We will change the wire color to purple for differentiation's sake. Go ahead and copy this code into the text format of your Tinkercad coding block. In this code, we include a servo library that is a pre-existing set of functions and objects and methods that will help us control the servo. Here we have a variable to know the potentiometer's position, and then we have a variable for the servo's position that we can set. We will create a servo object, which is just this object right here. In the void setup, we will call the given function attach by saying myservo.attach 9, which is the pin we connected the servo to on the Arduino. We will have in the void loop the potentiometer's position using analog read. Then we will have the servo's position set to a map where we convert the potentiometer's position, which is between the numbers 0 to 1023, to a number between 20 and 160. We do this because it's best to avoid turning the motor all the way to 0 or 180 degrees, which can cause the motor to jitter. Then we will tell the servo to move to that position by calling the .right function. There are a lot more activities that we cover in the slides instead of this video. Please go ahead and go through them step by step so that you get more practice and you can understand Arduinos better. When you finish the module, go ahead and take the post survey so we can find out how to improve this for your experience.